I'm Aaron Freeman, of course. The man on that very handsome man on the left there is the world's greatest living physicist, Dr. Nicholas Gross, lecturer in physics at Boston University. There he is. Oh, now you're in your civilian identity.
Yes. Glasses on and everything, yeah.
I would never guess. I would never know. I would never.
And AntMan in the same room at the same time.
I understand. Well, so now we're going to talk about the quantum realm, and you don't even know why exactly, because you are not a big Marvel Comics guy.
I can hold my own at a convention, but yeah. But I never got into the quantum realm, the Ant-Man. I never got into Ant-Man all that much.
Well, now this is what we were talking about right before we started, because no one understands what Marvel's quantum realm is going to be like. And I said, just as no one understands the actual quantum realm. But before we get to that, what the hell are we talking about when we talk about quantum physics and quantum mechanics?
Right. So Newtonian physics, which is extraordinarily successful at
all that whole gravity thing.
Gravity and forces. I mean, you build bridges with Newtonian physics. You build cars with Newtonian physics. And you build steam engines with Newtonian physics extended through thermodynamics. Right, but so that describes matter, or that describes things that are us size, right? Macro size things are a few tenths of a kilogram to a few thousand kilograms, or even maybe millions of kilograms. I don't my scale right.
Well, Newton will get you to planets. Newton will let you do gravity assists when you're going near a planet. I mean, Newton will let you do big, wonderful, amazing stuff.
Yes.
Land on
in a vast range,
right,
of scales, both distance and mass scales, right? But as we get to smaller, and what was discovered in the turn of the last century, the 1900s,
by James Clerk Maxwell.
Not really. So, but Planck.
I'm sorry?
Yes. So
Planck. Yes, Planck.
Well, and the thing I like about quantum mechanics, the thing I really like about quantum mechanics as a history of science guy, is it's a community effort. There's no one person who you go, that's the guy, right? Planck has his contribution, Einstein has his contribution, Bohr has his contribution, but you got to put it all together. It's not one guy. And
Well, I was going to say, there certainly has been for a long time a controversial topic. I found this.
Sure. Okay, you found that. Right.
Well, this New York Times, I'm sure early in the 20th century. Just only to make the point.
The 20s or the 30s.
Yeah, early.
And he's not and he's not denying. He's not saying no, it's all wrong. He's saying, I think there's a different interpretation. And people have been trying to interpret. So I think this gets into what you wanted to say. People have been trying to interpret quantum mechanics for a very long time. And one of the tricks is trying to find out what the rules are, right? And so, what are the underlying principles that get you get you something that predicts what happens in nature? And so if you look at things, so I think the other piece to what you're asking is you got to look at some specific phenomena. So if you look at light coming from atoms, so like a neon sign or other gas discharge tubes, sodium light, low pressure sodium street lamps that are very yellow. That kind of light, you look at those things and you get a different answer from what you expect from regular Newtonian mechanics. You get a different spectrum from what you expect from regular Newtonian mechanics.
No, okay. So let me. I'm gonna zero in a little bit on the Avengers because I want to hold the audience, maybe, but just for fun. But all right. So now the fundamental premise that we're all assuming of the Avengers version of the quantum world is essentially that within the quantum realm, everything is possible because all the normal rules, and this is really what you're saying too, that the normal rules that govern our world go kerflungy and things become impossible to predict in ways to which we are used.
Yes. So that is, you've got the Victorian statement, from a drop of water, I can predict Niagara Falls, right? I can say that Niagara Falls is there, right? And or and Newtonian mechanics of celestial bodies, right? I can tell me what the velocity and the position of something is, and I'll tell you where it is 100 years from now, 1,000 years from now, 1,000,000 years from now.
Right.
In the quantum realm, things become probabilistic. So I can tell you, well, that orbiting this atom might be over here, but it might be over there. And there's a 50% possibility that it's over here. It's a 50% possibility it's over there. Or there's a 90% possibility.
I believe you've just described. I believe you've just described the description of the quantum world that won a Nobel Prize in terms of the position of an atom around the nucleus, of an electron around the nucleus of an atom. Feynman's sum over histories. I have to go back. Feynman's sum over histories.
I think so. What I just described is a much simpler version, or not. Yeah. I won't say it's a vast precursor to that.
Yes,
right?
I mean, well, you're talking to me, so I know you have to give the kindergarten version. I do understand, but yes, I think
I'm not only giving the kindergarten version. I'm giving like an older version. This is like 3 steps before Feynman or something like that. Right. So and so Feynman takes that and starts to say, okay, how do I understand? How do I make the prediction of the probabilities that, given these interactions between in the colliders, right? These interactions between protons, that I'm going to get this kind of muon out, or as opposed to this kind of meson, or meson. Did I make that up?
Meson.
Meson. Yeah, okay. Now, of course, this kind of particle out as opposed to this kind of particle out. And
of course, when you start talking muons, I start thinking neutrinos because I'm here in Chicago with Fermi Lab.
Okay, right,
Muon neutrinos, and we could go on another show we could do about that. Okay, but here's another thing that's really important as I talked to Dr. Nick Gross, the world's greatest living physicist lecturer in physics at Boston University. And if you're enjoying our little chat, please like the Excitable 8 page here on good old Facebook, and head on over to Science Today, where you can check out various conversations with Dr. Nick, the world's greatest living physicist. But another thing that Marvel needs to have in its quantum world are multiverses, or do you say is the multiverse? Now, what in the blue-eyed buck neck and heck is the multiverse, or is a multiverse?
So I'm not up to speed on the current research on this and where people stand on this. Right now, it's at least purely theoretical, if not purely speculative. Okay, and those two things are different, right? The theoretical is.
I mentioned the Marvel comic book universe, right? I did mention that.
Yeah. But the multiverses, or this idea of multiple universes, exist, and the difference between theoretical and speculative is theoretical is I've worked it out and we just can't do, or we haven't done the experiment yet. Speculative is I'm making some wild guesses right now about what might happen, and I think it's this. So this is sort of this is part of Feynman's sum. Is a little bit like Feynman's sums over histories, right? So you've got this quantum idea of probability. So the key is though that. So I look at an atom. I ask where the electron is orbiting, and I can work out the probability that when I take the measurement, the probability that it'll be on one side or the other. But then I take the measurement, and I get an answer. And at the moment I take the measurement and I get an answer, I know where the electron is. I don't know where it is after that, and I go back to my probability. So the key is that when I do that, when that happens, I've almost made a choice. I've pinned the universe down, at least that part of the universe down to a point, right? And said, aha, the electron's here. And that could be a decision point, right? That could be a branching point, because I could have gotten a whole host of answers, all of which might be equally probable.
Okay.
And so the possibility is that the answer took me along this path, but I could have gone along this path, right?
In terms of predicting where the electron could have been.
Yes, and in terms of the history of the universe.
Say it again.
In terms of the history of the universe.
All right, say that again slowly, please.
Okay, so I've got the electron could be in any one of my 10 fingers, right?
Got it. Lovely
right.
Fingers, soft. You must take good care of your hands.
But so, before I take the measurement, I don't know where it is.
Okay.
So there's so there's a 1 in 10 probability that it's in any one of my fingers.
Got it.
Now I take the measurement, and I find out that it's in that finger.
Got it.
Now I know something about the universe, and now my everything after this point in our universe says at that place in time there was an electron.
There's one thing that we know. We know that right. There's one thing we can be certain of, that at that point in that time, that electron was right there.
Was there, right?
We will move on. We can move on from there, basing on that.
Right, but there was an equal probability it could have been in all these other places too. And if that's the case, then I could have gotten this guy. And I'm not going to put my finger down. Maybe this guy, right? Or my pinky. I could have got my pinky as an answer. And so there's another universe where that's the answer, where that electron was there. And that would have a different history.
Why is there another universe? Where do we get the fact, this notion that there is another universe just because?
This is the speculation. I mean, this is the...
Okay, I got it. So and then what gives it, why is it what gives that speculation any currency at all?
That there's nothing particularly physical about the measurement I made. Sorry, there's nothing special about the measurement that I made that says this is the only answer that I could have gotten. The interpretation of quantum mechanics is all of those. It's not just that I don't know enough. Like when you roll dice, you don't know enough about the system, right, to be able to tell whether it's going to be a 1 or a 6. Right? You just don't know enough about how hard the dice were thrown and what the corners are doing, and
right.
In
but
this case,
the probabilities of which numbers will come up.
Sure, but it's that the variables are, there's too many so
to predict accurately.
Right.
Over time, you can say that it was there's a higher probability.
Right. And there's some interpretation of quantum mechanics that are like hidden variable theory. So where you say, okay, it's just that we don't know enough variables And if we can find the underlying variables, we'll be able to predict everything becomes deterministic again.
Yeah.
But the current interpretation of quantum mechanics and the interpretation of quantum mechanics that your hero, Feynman, is want to quote, says, nope, it's all probabilistic. These two paths were equally probable, and I could have gotten either of them. There's nothing special about the one I got.
So when we say the sum over histories, as I understand it, what really we're talking about is that to try to talk about the position of an electron relative to the nucleus of an atom, you would assume that the electron gets to any one position by all probable paths, and that the calculations have to do with the sum of the probable paths as opposed to its history where it was a second ago. And so calculations are assuming that all possible paths are possible, and then you decide. Then you can calculate the probability that it'll be on any one particular place, but not based on where it was before.
Yeah. So the idea in Feynman is that, right? I mean, I think you've described it pretty well, but it's that you know one point where the electron was, you know the other point where the electron was. What you don't know is what happened in between.
Right. And
so to understand what happened in between, you've got to sum over all possible paths. Yes.
They use to take the sum of all possible paths and then calculate the probability of any given path.
Don't violate.
Right. Yes.
That don't violate physical laws like conservation of energy.
Right. Okay. Right. The basic stuff. Okay, you can't. Even Marvel is not, as far as I know, is not violating the conservation of energy. But I'm not sure.
Yeah, the whole AntMan thing kind of violates conservation of mass, and that makes me a little crazy. But
whoa! What did you explain, please?
Well, so I don't know how he shrinks. Right? Does he get rid of mass? Do all of his atoms become closer together?
Wait, excuse me, as a well-trained comic book scientist.
Yes, okay.
As a man who has studied comic book physics for many years, let me just say to you, neutron stars. That most of you and me and everything else is empty space, 99 point whatever it is % empty space. And AntMan if he can eliminate the empty space between the electrons and the nuclei. Why are you looking at me? Most of the volume is empty space.
So do you have a checkbook?
Like, now tell me what is wrong with that. That's what they say in the comic books. Now tell me what's wrong.
You understand that simply because you haven't run out of checks in your checkbook yet doesn't mean you can still write checks, right? Oh, he's mad at me. Oh, where do you go?
Right here.
Oh, okay.
No, I had to turn my wife's phone was beeping. I was turning it off. Sorry. But you weren't.
Okay. So I. It's
so you said that you're making fun of me. You're making fun of me.
I mean, it's not like you just put something there in that quote unquote empty space. I mean, yes, there are things that can pass through it, but I can't bring the atoms closer together.
That's because you don't have the AntMan suit. That's the whole point to the suit. For crying out loud, do I have to explain all this to you? But that's, I mean, okay, but in theory, I'm serious.
Unobtainium, what's it? No, it's not unobtainium. The Wakanda.
Oh, the vibranium.
Vibranium, right? Yeah, so we don't have any vibranium either.
But wait,
right?
But let me just say, in theory, if one had a suit that was able to reduce the space, what would stop the suit? Well, no, more importantly, what would the suit have to do to be able to reduce the space between electrons and nuclei such that the total volume of the material would shrink, would lessen?
So this is my I'm going to quote my so the verse I'm more familiar with is the Star Trek universe, right?
Okay.
And so from Next Generation, Q,
Of course, Q. Yes, Q violates everything. Okay, Q violates everything.
Change it to. I'm going to riff on him. Change the electric constant in the universe, right? Change the electric permittivity in the universe, and you just and that changes the force. So that will bring everything together. So if I change how electric force works.
Yeah, well, because and it's the electromagnetic forces that allow things to feel solid, even though people like you claim to us that they're really just clouds. But it's the force of electromagnetism that does not allow my one hand to go through the other, even though they're both.
And it controls the size of the electron's orbit.
Yes.
So the electric forces. So the thing about quantum mechanics is all the forces that we know about still are there. It's just that they obey a slightly different type of mechanics.
And is that because of the other forces, the nuclear forces, small and weak? No. Okay.
So no, it's sorry, I didn't mean to just like shut you down like that, but no, it's the nuclear forces are going to be there and doing their thing, but the outside of the nucleus, it's the electrostatic force that keeps the electron in orbit around the nucleus, and that's one of the constants that sets the distance.
All right. So wait. So you
change the charge, the fundamental electric charge, right? I could increase the fundamental electric charge between the protons and the electrons.
And if you increase that charge, that would, or you would walk about if the suit. Let's not forget the suit that allows us to get to the quantum realm. If that muck about with the electric charges of the person wearing the suit, that could allow a lessening of the spaces between the atoms, and then you and the suit could shrink proportionally.
Yes. And what I don't know is I don't know if that speeds up all the processes too. So if I did all my electrochemical like ADP to ATP, right, my respiration, that sort of thing, and let's see. So does the suit have its own oxygen supply?
Well, it's got a helmet, so I don't know.
Because it's got to have your oxygen. Whatever's happening, the oxygen that you use has to be shrunk too.
Yeah, and you'd have to be able to get oxygen. If you were that small, you'd have to be able to get oxygen molecules that were at that point the size of basketball courts.
Well, in the quantum realm, certainly, yeah. I don't.
That's the thing. If you show that,
I'm just thinking when he shrinks down to like ant size or something like that. So, well, I don't know what happens when you shrink beyond the.
But let's just say for a second, okay? Let's talk about energy. So we have our suit that has the ability to change the local electromagnetic field, the workings of electricity in its local area, the area of the guy wearing the suit. To achieve such a feat would, I assume, require some pretty impressive amount of energy to overcome the normal operation of the electromagnetic field of the universe.
I'm trying to think whether that's.
I got to admit, I did not find a Marvel comic book that talks about this about the amount of energy that it requires for the suit.
I have to think about what if you have to actually. I mean, one of the ways we can think about this is whether you have to actually put energy in to compress each of the atoms, or if
you'd release energy, release electromagnetic force.
Put it into like, if I'm going to compress the atoms, am I putting energy into them?
Well, what's the alternative? I mean, but the mechanism by which I'm saying the mechanism.
I'm doing something that an omniscient being would do, right? I have no idea how that works. And I'm changing one of the fundamental constants in the universe. I don't know if I need energy to do that, right? Or is it just a dial that I turn? And so if I want to, mind you, so and this is less speculative, but still speculative, that during the Big Bang, there's some idea that there were all these other universes were created.
Yes.
Right, and that we're just one bubble.
Right.
And
they exist in dimensions that are here. There exist other universes exist in dimensions that are right here amongst us, but we can't interact with.
Sure.
I mean, one of the theories. Yes.
Yes. Right. But one of the things that I don't think has been that even the invention of the Higgs, or the discovery of the Higgs has solved is, how do I how are the fundamental constants set? Right? How is the speed of light? Does the speed of light have to be what it is?
Discovering the Higgs confirmed our notions about how particles acquire mass.
Sure, but the Higgs has its own mass,
right?
And what says that Higgs has to have that mass as opposed to this guy, right? And if I have a universe in which the Higgs has a different mass, and it sets the mass, but it doesn't set the charge, I think. And then you've got all the other constants. So there's this, so there's this weird thing where you could imagine that there are different universes that have different constants, and so scales are different in those universes. What I don't know then is, suppose I decide, okay, I want to change the fundamental constant in my universe. What do I got to do to do that? I don't know. That's like I'd be making something up. So you could imagine. Yeah.
So you and I met at the customer,
yes,
the Rubik Improv Science Group, and at that at the meeting we were at in Chicago last September, Ann Murphy, who is the public outreach director for the National Academy of Sciences and runs this wonderful has a wonderful phone number, 1-800-NEED-SCI, people who are doing science.
Right.
And so people ask her, well, are they calling you to make sure the science is accurate? And she said, well, we like the A word, but we're not obsessed with that. So you want it to be want science to be plausible. Right. Plausible, that's nice. Plausible is good. We like that. But we like to think about science fiction that is inspiring. And I'm just curious. Well, obviously, at least certainly my version of how the Marvel comic universe works is not necessarily in keeping with what people like you know about it. But so is there any use to it? What about this business about inspiring? Because my guess is that more people have inquired about quantum phenomena because of Avengers and Avengers 4 and AntMan than probably at any point in human history.
Sure.
I mean, because they have that hundreds of millions of people see that thing, and I don't think there are hundreds of million people who even know who Robert Richard Feynman is, much less have listened to any of his lectures. What? You're not buying this. You never buy anything I see. Every time I see.
Yes. No, I think you're right. I think there's a lot of people who are been exposed to the quantum realm and because so what's your question? I guess is the
you as a man who spends his time teaching physics to folks who aren't necessarily physicists. Is there a utility to products that merely inspire you without merely make you curious about it, merely inspire you to think about something without actually teaching you anything seriously good? Is it seriously academic? Is there utility?
Sure. I mean, about a lot of activities. I mean, there's a lot of like museums in general, science museums in particular, are as much about inspiring people as they are about they try and have a teaching mission, but in terms of like rigorous understanding, you don't expect somebody to go to a museum exhibit on butterflies and come out with a rigorous understanding of the life cycle of Morphididius, right? And so that they come out and they go, butterflies are cool. I want to learn more about butterflies, or I want to learn more about the stars, or I want to learn or this quantum realm is cool. I want to learn more about that. Sure, right? And
well, there's
lots of Marvel. There's lots of Marvel fans in the sciences. I mean, it's not.
Oh, sure. Well, I was just saying that just in preparation for this, the thinking about, because of this silly movie, I went back and my wife and I sat in bed and watched old Richard Feynman lectures.
Oh, okay.
I mean, and that's what in the best world, that's what you hope science fiction would do, that it would inspire people to remind, there is quantum mechanics. Okay, maybe it's not, maybe Ant-Man's not going there. But it is possible. There is such a thing. And when you actually do a little bit of just watching a few even YouTube videos on it, watching Feynman.
And even just to say, well, that's nice, but it's not really how it works. And let me tell you how it works, right?
Yes,
and
absolutely. And I mean, my overall impression, in fact, is that what little I know of the actual quantum world is arguably weirder than the stuff that shows up in the comic books. I mean, the actual world is really, really bizarre. And when you teach first years, right? Physics first year students?
Oh, well, yes, undergraduate. So it's a first year. It's a sort of intro course. Yes. So sometimes they're like third years, but they're not physics majors. So this is their first exposure to college level physics. Yes.
So do most people come in with a kind of Aaron Freeman kindergarten understanding of quantum mechanics? That it's weird, and Richard Feynman said something about it, and Werner Heisenberg said something about it, and
I wish, right?
Really,
that they came in with that much understanding.
Huh? So even at good schools, you mean? So people get.
And some people come in with, they come in with an understanding of the Bohr model.
Niels Bohr.
Yeah.
Famous,
right,
yes.
so the Bohr model of the atom, but it's very school.
I don't know what the Bohr model of the atom is.
Oh,
I couldn't come to Boston University.
So it's you probably do. You just don't know that you know. It's the sort of, you've seen pictures of this. It's the fixed orbits model.
Oh yes, the atom as miniature solar system.
As a miniature solar system, but the planets are on very specific distances, or the electrons are at very specific distances.
Okay,
that are fixed, and they jump between those distances. Right? They can't move in sort of whatever way they want. The Jimmy Neutron version of this, right? Of the Bohr model. The other problem is that really you have to eat, before you get to the fun stuff, you have to eat your vegetables. So in order to understand the quantum nature of things, I have to be able to talk about electrostatic energy, right? And I have to be able to talk about circular orbits, and I have to be able to talk about those sorts of things that are all classical mechanics concepts. So I think this is part of this is the challenge is you first wrap your brain around classical mechanics, around Newtonian mechanics, and you do all the hard work, and then somebody says, hey kid, come here. I
got a theory right here for you.
Yeah. And everybody goes,
that's it. I got a nice universe right here. You got a nice universe. Wouldn't you like another couple of 100 universes here?
and then I go, no, you don't. you don't get to pick whatever energy you want. It's, the energy is fixed, and you don't get to. There's these there's and all this deterministic stuff that we were telling you about. That's all out the window. But I also like to say that it's not that we throw Newton out. I mean, Newton doesn't go completely away. Quantum mechanics extends Newtonian mechanics. So it takes Newtonian mechanics and makes it, or rather, it says, okay, when you're working with macro stuff, this Newtonian mechanics is but more fundamental when I'm working at this smaller level.
But this gets us back, I think, which is a kind of fun place to be, I think, which is when we talk about the obsession that you and your ilk have for a single unified theory, that the unified theory of matter would unify quantum mechanics with Newtonian physics. Oh,
so Newtonian mechanics and quantum mechanics are unified already. I get Newtonian mechanics from quantum mechanics when I take the mass is large and the distance is large.
Then what would the unified theory is going to unify quantum mechanics and what?
Oh, so the big thing, the big problem is gravity.
Well, okay.
Gravity's the mass. Oh, I see. And,
well, that was what I was saying.
It's not Newtonian mechanics. You want to unify quantum mechanics with it's Einstein. It's gravity. Okay. It's general relativity. So what people have been struggling with is taking the machinery of general relativity and applying quantum mechanics to it. And I really don't know much about why it breaks. What's interesting is special relativity was dead easy. So Dirac did that in 1930. And in fact, that all of the fundamental physics that you, all of the particle physics that you do, that people at your favorite place, Fermilab, do, all of that is not only involves quantum mechanics, it also involves special relativity. They just don't tell you about that, right? Because that's not the exciting part.
Well, it's probably better that they don't tell me, because it would just make me feel even dumber. That would make me feel dumber than I normally do. But on that, let's just say though, but it is good to know. And one of these days it would be fun to talk about the difference between general relativity and special relativity, which are really significant and interesting, and both of them come out of the same.
Sure, right. And we can reference Interstellar.
Another great film. All right. Well, so this is a wonderful. Now Friday's our date nowadays, right? Friday's our date
nowadays. Yes.
Friday's our date nowadays with the world's greatest living physicist, Dr. Nicholas Gross. As you can see, that beautiful man right there. And so, Nick, we will talk to you next week, and we'll figure out something interesting and cool. But I think Interstellar would be really great, and general and special relativity. So thank you all. Thanks for watching YouTube. Thanks for watching on Facebook. I love you, Nick. Have a great weekend, brother.
Okay, you too.
All right. Oh, that.